I want to start with a discussion of some of the mathematics that we're going to be using here. In the beginning, as we're talking about our rates, and we're talking about a delta, maybe a partial pressure over a delta temperature or a delta molarity, that's called a differential rate law. So that would be considered a rate. So if that was, say, the partial pressure of hydrogen, that would be considered the rate of hydrogen. Now, the terms that show up in this are rate, the rate constant, and either a concentration or a partial pressure. And we can have zero order, believe it or not, it could be zero order, primarily because whatever the substance is not involved in the rate determining step. And in that case, anything, I'll go ahead and plug it in here, but anything to the 0 power is 1, so we don't normally write that down. And then we would have first order and then second order. Now, a common thing that is confused, and I've done it myself, I've looked at data and I've grabbed the wrong formulas. I'll see a concentration and a time and I'll try to convert it to a rate. Don't give in to that temptation. Circle what you have. If you're given a rate and either molarity or a partial pressure, and write those symbols above the numbers, the values you're given, then you know you're dealing with one of the differential rate law equations. If you're given time, excuse me, and molarity or partial pressure, then we're going to be dealing with what are called the integrated rate law expression. Now, to make the leap from here to here requires calculus. And honestly, it's not that difficult to calculus. If you're in calculus right now and you want me to show you this, I can do that, no problem. But most of you aren't quite in calculus yet. You're likely in pre-cal or something like that, and it's not necessary for the discussion. So we're just going to say, from here to here, the miracle of calculus occurred. And we will simply use those equations. But how to know when to use those equations depends upon the variables that are provided in the problem. Again, time and either molarity or partial pressure, we use the integrated. And if it's rate instead of time, we'll use the differential. And it's quite easy to get those confused. So you want to pay very close attention to that. And I have another summary chart of this at the end of the notes, so you have good reference for when you're working on your homework. So when we're going to start first with the differential rate law expressions and the mathematics and determination of that. So we're dealing with rate and either concentration or partial pressure right now. We're going to have tables of data, and the data represents a variety of experiments. So we're going to compare the results of multiple experiments. Now, any well-designed experiment, which is why I really need to do the videos for you, by the way, because I want to find out if flip is effective. And if I use other teachers' videos or rely on other teachers' videos, then if there's a change, either for the better or for the worse, I won't know if it was the flipped process or if it was the difference in the teaching that resulted in that. So I'm hoping to, it's difficult truly in education to do this, but I'm hoping to keep it as one independent variable, that is the flip, the change in times, and then we want one dependent variable. And the rest, man, I have a typo here. We want one independent variable. We want one, we'll have one dependent variable. The dependent variable is going to be time, or we'll go ahead and call it rate. Usually it will be time, and then we would calculate a rate, but we can leave it at rate for now. The other variables, the other concentrations, all other concentrations, we need to keep controlled. Okay, so I filled in those blanks wrong when I was typing too quickly. Sorry about that. So again, what our goal is to have, we're going to set it up. So one molarity, so concentration of one substance, is independently varied between two experiments. We will have time, or the rate, depending on how the experiment is designed, will be our dependent, and then all other concentrations will be controlled or held constant, so that we can isolate the effect of A on rate from the other effects. And we've mentioned this many times. We'll be dealing primarily with molarity and partial pressures if it's a gaseous system. Pay very, very close attention, because we're going to be dealing minutes, seconds, but I know I've seen at least a few that are in hours. And honestly, there are reactions that take centuries to occur, not reactions we can study in the lab. But pay very close attention to the units that we will be using. Now, in this case, this is our data. We have our balanced equation here, but this is not an elementary step. You would know it's an elementary step two ways. One, the problem would say, determine the rate law expression for the following elementary step. Because you know, we can't just look at a reaction and know. Now, we can look at a reaction and speculate. There's an arrow there. We can look at a reaction and speculate, but we can't know for sure in that case. So it would tell you. Or you're looking at already a list or that mechanism of elementary steps. So the fact you're looking at a mechanism would give that away. Now, in this case, the problem very clearly states that we're measuring initial rates. We're measuring them in millimeters of mercury per second. Now, don't forget that a millimeter of mercury is the same thing as a torr, and that might be a little bit easier to write. You can interchange those if you want. That's no big deal. Okay. Now, our goal is to set up experiments where if I want to find the order with respect to NO, I want NO to change. I want to have that independently varied, and I want to keep my partial pressure of hydrogen controlled. So I want to compare two sets of experiments where partial pressure of hydrogen is constant. So we can look at this and this, it's constant, and NO varies. And so I'm going to take a ratio of those two rate laws. Well, let's start with what is a reasonable possibility. It is reasonable, I hope, that our rate could be, I'm not saying it will be, but could be dependent on the partial pressure of NO to some power that we don't know its order yet, times the partial pressure of H2 to its order, and we don't know that order yet. And those orders can be 0, 1, 2, 3. Really, they can be fractions, they can be half, and in real life, you'll see negative ones. We're not going to come across those, but we will see halves. Now, what I want to do is I'm going to take a ratio of those, because if I look at one experiment, we see that if I just plugged in the data, I have two unknowns. Both X and Y are unknown. So the approach is to take a ratio. It's why I am very glad that AP kept rates in their new curriculum, because it's one of the times where you are able to begin to get an introduction into data analysis, which is very, very important. So I'm going to take a ratio, and you notice I picked 4. I'm going to take 4 over 1. And the only reason I took 4 over 1 is because if you take the bigger number and divide it by the smaller number, the mathematics typically shows that more obvious. You don't have to do that if you don't want to. You've got your calculator for these typically. And that's going to equal a ratio of rate laws. And so I would have my rate constant. Now, in place of my partial pressure of NO, I'm going to put 300 to the X, and then I'm going to put 400 to the Y. And likewise, I'll do it for the other. And this time it's 150 to the X, And again, it's 400 to the y. Now, you don't have to show all of this. I will be doing that so that you see where I obtained this equation. You can streamline it a little bit and not show what I'm about to cancel. Now, the only time that K changes, K is not dependent on concentration. It's dependent on the reaction that you're dealing with, we'll see, and it's dependent on temperature. So it changes with temperature. So this experiment, we can't be changing the temperature here, or we've introduced two independent variables, and we won't know if our effect is due to temperature or our partial pressure. So our K does change with temperature. Since temperature is constant, K is constant. So I'm going to cancel the K. And since we've set this up so that hydrogen was a control variable, I've narrowed this down to one equation and one unknown. Now, you all know how to do this algebra, I hope. If you don't, if you have trouble with this, you need to come see me. But I would end up with 4.12 is equal to 2 to the x. Now, I hope you see that x is likely 2. And that's what, if you put the bigger over the smaller, you can get that. But if it's not so obvious, what you do, if you haven't had your logs yet, which I think most of you have, you take the log of the one without the power, divide it by the log of the one with the power, and that will equal the power. And if you do that division, we find that x is equal to 2. And that means it is second order with respect to NO. So it's a second order reaction for NO. Now let's move on to the next part. Now we need the order with respect to H2. We're going to proceed just like we did before, but this time we're going to compare these two experiments. So it's 1.34 over 0.66. And that is equal to, again, I'm going to be really explicit here. Now, we know this order now. That's not an unknown. And I'm going to go ahead and put that in because there are times when you have one of the substance that changes every time. So once you have its order, you can keep that in there and it would just add a little bit of extra algebra. So if this wasn't a 400, for example, and I did this while I was talking, I grabbed the wrong one. I wanted 300 here. If this wasn't a 400, for example, you could just keep that algebra in. So let me check. I've got the 134 with the 400 and the 300, so we're good to go. Now, K's cancel. Whoops, wrong one. That cancels, fortunately, simplifies our math. We could have done a little more algebra if we needed to. And what we get is 2 is equal to 2 to the y. So y must be equal to 1, and that means it is first order with respect to our hydrogen gas. Now, I'm going to go ahead and stop now, and we're going to pick up this problem as we continue our discussion of the differential rate law expressions.